We're ready to start section 4.5 on the chain rule. As you might imagine, it gets a little more complicated when you have more than one independent variable. We saw that the chain rule was hugely important in calculus 1 and 2 in finding the derivative of composed functions, functions inside of functions. In the case of multiple independent variables, there are various forms that may require an application of the chain rule. There won't be one simple rule, well, not simple, but there won't be one rule for the chain rule. It will depend on the structure of what you're trying to take the derivative of. Let's take a look at two examples here in the center of the introduction. Suppose you have a function g of two independent variables, x and y, and you want to compose it with a function of one independent variable, f. So you can apply f to the output of g of x and y. But because g is a function of x and y, then ultimately f also becomes a function of x and y in a sense. This is different, however, from the composition next to it. In the composition next to it, we have a function of two independent variables again, called g. But in this case, the two variables it depends on, x and y, are themselves functions of another variable, t. In this case, we have a function of two variables composed with two functions of one variable. The form that the chain rule will take will change depending on the form that you have. Let's go ahead, share the screen, and we'll get started. One of the things that you can do when applying the chain rule is make sure that the domains and ranges of the composed functions match in the order in which they're composed. If you have a function of a single variable, you can put a function of multiple variables inside of it, since the output will be a single function. However, you can't go necessarily the other way around. You can't put a function of a single variable by itself inside a function of a multiple variable. You need to make sure that the domain of one gives the appropriate range output so that that range becomes the domain of the outside function. When we're thinking about this, we're going to have three learning objectives. We're going to find the chain rule for one or more, well, two or more independent variables. Then we're going to use what are called tree diagrams, which will help us to analyze the structure that we need to apply the chain rule in. Then we'll be able to find implicit differentiation of a function of two or more variables. We want to start with the chain rules for one or two independent variables. In this case, we're going to start with a function of two variables composed with two functions of a single variable. In this case, we're going to allow g to be a function of both x and y, but we're going to allow its independent variables, x and y, to themselves be functions of another variable called t. Ultimately, this makes g also a function of t. The chain rule in this case looks like the following. Because z, the output of the function g, is ultimately a function of a single variable t, since both x and y depend only on t, then we can use the regular first derivative of z with respect to t, using the italicized letter d and not the partial symbol. However, to find the derivative of z with respect to t, we need to take the partial derivative of z with respect to x and multiply by the derivative of x with respect to t. Now, again, this is Leibniz's notation, and it works, which is why we do it. But keep in mind that these are not really fractions. These represent derivative operations, either the first derivative, normal derivative with an italicized d, or they represent a partial derivative of a function of multiple variables. In a sense, though, what students tend to think is that the partial with respect to x and the partial or the derivative differential dx cancel. They don't, they're not fractions, but in a sense, it does sort of give us a derivative of z with respect to t. But that's not all that z depends upon. Z, or the function g, also depends on the independent variable y. Y itself, though, is a function of t, making y both an independent variable for g and a dependent variable based on t. So we add to that the partial of z with respect to y multiplied by the regular derivative of y with respect to t. If it is a function of one variable only, we use the italicized letter d. If it is a function of multiple variables, 2 or more, we use the partial symbol. You can either apply this using z for the dependent variable of the outside function, or you can use the name of the function g in order to accomplish this. Let's go ahead now and take a look at an example. In this case, we're given that z is equal to the function f depending on two independent variables, x and y. Its expression is x squared minus 3xy plus 2y squared. X, however, depends on the value of t. So x, as a function of t, is 3 sine of 2t. Y is also a function of t, and it is 4 cosine of 2t. We want to go ahead and find the derivative of z with respect to t, not the partial, the first order derivative, regular derivative, with an italicized letter d. That's because if both x and y depend on t, then ultimately z, or in this case f, will depend only on t as well. Let's go ahead now and apply the formula. The first thing that we need to do is we need to find the partial of the outside function with respect to one of its independent variables. We'll start with x. So when we're looking for the partial of z with respect to x, this will be given by 2x minus 3y. We want to take that and we want to multiply it by the derivative of x with respect to t. When we take the derivative of x with respect to t, we come up with 6 cosine of 2t. This term that you see here boxed up is going to become down here. Let me write dz dt. This is going to become 2x minus 3y multiplied by 6 cosine of 2t. If it bothers you to have the 6 in the middle, simply move the 6 to the front of that expression. Now let's go ahead and find out what the partial of z is with respect to y. When we look at the partial of z with respect to y, then we get the following. The partial of z with respect to y will be negative 3x plus 4y. Then we need to compute the first derivative of y with respect to t. This will give us a negative 8 sine of 2t. When we multiply those two factors together and combine them with the other, we get the following. Negative 3x plus 4y multiplied by a negative 8 sine of 2t. This gives us an expression for the first derivative of z with respect to t. Notice in this case that we still have both x, y, and t in the equation. Could we write it explicitly in terms of just t? The answer is yes, we can, because we have the expressions for x and y up at the top. We could rewrite this then following that formula as 6 times, and then we would have 2 times x, which is 3 sine of 2t, which would give us 6 sine of 2t, minus 3 times y, which is 4 cosine of 2t, which would give us minus 12 cosine of 2t. And then for the next part, we would have minus 8. Did I finish that? Oops. Yep. I forgot the cosine of 2t on the outside. Minus 8 times negative 3 times x would be negative 9 sine of 2t. And then the plus 4y would be plus 16 cosine of 2t. And this would be multiplied by sine of 2t. In this way, you can see that it is, in fact, a function of a single variable t, which now justifies our use of the italicized letter D. If you want to play around with trig identities, you could probably write this in a different form. Whether or not it would be simpler is not clear. Let's now move on to example 2. In example 2, we are given a function z equal to x times the exponential e to the xy power. We're told that x is a function of t, x equals t squared, and y is also a function of t, t to the negative first, or 1 divided by t. We now want to go ahead and do what we did before, using method 1, which is to apply the chain rule that we saw before. So if we're going to apply the chain rule that we did before, we are going to compute z as a function of t, which gives us the first derivative with the italicized letter d. We take the partial of z, which is a function of 2 variables, with respect to x, and multiply it by the first derivative of x with respect to t, since it is a function of only 1 variable, t. Then we add to that the partial of z with respect to y, using partial notation because z depends on 2 independent variables in its first iteration, and then multiplying this by the first derivative of y with respect to t, since y depends only on t. Go ahead and pause the video, work this out, then turn the video back on so we can compare. In this case, I went ahead and did all of the chain rule within 1 line. I took the partial of z with respect to x, which invoked, of course, the product rule, since both the factor x and the factor e to the xy both depend on x. That gave me 1 times the exponential e to the xy plus xy e to the xy, applying the chain rule on the second term. Then I need to multiply all of this, of course, by the derivative of x with respect to t, which gives me 2t. The second term starts with the partial of z with respect to y. Since only the exponential factor depends on y, it considers the x a constant. So it becomes x times x e to the xy, or x squared e to the xy. Then I need to multiply by the derivative of y with respect to t, which turns out to be a negative 1 divided by t squared. The next thing I did is to replace the x with t squared and the y with 1 over t so that I could get it written as an equation in terms of only t. In this case, by replacing them, I was able to work out the algebra to come up with t e to the t as a factor, common factor, multiplied by the expression t plus 2, which is far simpler in form than the one that depends on x, y, and t. Which one you want to leave it in depends upon your instructor and the situation that you have. Sometimes leaving it in one form is simpler than the other, but it's not always one form or the other. You'll have to make a judgment call based on the situation you have. Let's now think about another method of doing this one. We could, if we wanted, have taken the original equation, which was xe to the xy, and we could have replaced the x with t squared and the y with 1 over t from the beginning in the expression of z. In other words, coming down here, I could have taken my z equal to xe to the xy, and I could have written this as t squared e to the t squared times 1 over t. In this particular problem, trying to put the tail on my t, this would give me t squared e to the t. Now I can take the first derivative directly as it is written only as a function of one variable. In this case, we again apply the chain rule, which would give me 2t e to the t plus t squared e to the t, which when I factor out the common factor of t e to the t, leaves behind a 2 plus t, or t plus 2. And I get the same result that I got with the first method. In this case, the second method was far simpler. Unfortunately, you will never know which method is going to be simpler until you try it. In some cases, method 2 might be a nightmare, but method 1 is doable. In some cases, method 1 is longer and method 2 is shorter. Let's now turn our attention to example 3. In example 3, we have more complicated functions for x and y as functions of t. X is equal to the natural log of t squared, which has composition of functions within itself, and y is equal to the sine of 4t, again with a composed function. Z is given by x squared y cubed plus y cosine of x. In this case, chances are applying method 2 would probably be more challenging, since the representation of z would get a lot more complicated. It could, however, be done. We're going to go ahead and apply method 1 here using the chain rule. The chain rule in this case, since both x and y are functions of a single variable t, and since z depends only on x and y, we can get z written as a function of t only. That makes it the first derivative of z with respect to t using the italicized letter d. This becomes the partial derivative of z with respect to x multiplied by the derivative of x with respect to t, plus the partial of z with respect to y times the derivative of y with respect to t. Go ahead and pause the video now to work this one out, then turn it back on, and we'll check each other's work. When we apply method 1, we find the partial of z with respect to x, which gives us the quantity 2xy cubed minus y sine of x. Then we multiply by the derivative of x with respect to t, which invokes the chain rule for functions of a single variable, where the derivative of natural log is 1 over the argument multiplied by the derivative of the argument. That will reduce to 2 divided by t. Then we add the partial derivative of the function with respect to y, the other independent variable. In this case, that gives us the expression 3x squared y squared plus cosine of x. This is then multiplied by the first derivative of y with respect to t. This is a sine function with an argument of 4t, so the chain rule gives us 4 cosine of 4t. And you can see the final result highlighted here in yellow. Notice that this one was not as difficult with method 1. It seemed to flow much better. It is written in terms of x, y, and t. You could, if you'd like, go ahead and write it all in terms of t by substituting natural log of t squared for x and sine of 4t for y. In this case, however, I think it is probably better to go ahead and leave it in terms of x, y, and t. If you were to write it in terms of t alone, it becomes this expression that you see in dark blue. This is a far more complicated expression. We have 1 over t times the quantity 4 natural log of t squared sine cubed of 4t minus 2 sine of 4t sine of the natural log of t squared, then plus 4 cosine of 4t times the quantity 3 sine squared of 4t times the square of the natural log of t squared plus cosine of the natural log of t squared, which seems more confusing and less clear than if we had left it in the form that you see up above. However, this is very dependent on the particular instructor that you have, so make sure you check with your instructor to see what their preference is. We now want to consider a special case. The special case is when y itself, one of the independent variables of the outside function, is also a function of x. So in this case, we have simply g or z as a function of x and y. X is simply x, not a function of another variable, and y as a function of x. Let me write that down now. We have g of x and y, and then we have just x, and y is a function of x. When we have this situation, the form of the chain rule is the same as what we've seen before. Because g depends on 2 independent variables, we use the partial of g or z with respect to x first, and then the partial of it with respect to y. We multiply the partial with respect to x times the derivative of x, well, it's not a function of anything else, with respect to x again, and the partial of z with respect to y times the partial or derivative of y with respect to x. Now, it may look funny to write dx dx, but what it means, of course, is actually the derivative of x with respect to x. In other words, if you look at this notation down here, where I've pulled what was in the numerator down to the line, it makes it more clear that we're applying the derivative operation with respect to x to the function y equal x, and the derivative of x is just 1. So again, this meets our expectations that dx dx would in fact be 1, and it is. Since it does, then the formula simplifies to give us the following. The partial of z with respect to x, and again, dx dx is 1, so we don't write it. The partial of z with respect to y times dy with respect to x. Now, let's go ahead and apply this in example 4. In this case, z is a function of both x and y. X is not a function of any other variable. Y, however, is a function of x. You can apply the chain rule in the original form, keeping the dx dx, if it makes it simpler for you to use the rule and memorize how to apply it. Go ahead and pause the video now, work it out, then turn the video back on. In this case, I'm applying method 1 again by applying the chain rule. I find the partial of z with respect to x, which gives me 2xy to the 4th. Then I multiply by the derivative of x with respect to itself, which just gives me a 1. Then I add to that the partial of z with respect to y, which gives me the expression 4x squared y cubed minus 2, multiplied by the first derivative of y with respect to x. In this case, I have to apply the chain rule for functions of 1 variable, giving me the derivative of the outside cosine, the inside still x squared, multiplied by the derivative of x squared, which is 2x. In this case, note that there is a common factor of 2 in the first factor of the second term, and you could take that out. Then, if you want to write it all in terms of x, you can replace y with sine of x squared, getting the expression 2x sine to the fourth of x squared plus 4x cosine of x squared multiplied by 2x squared sine cubed of x squared minus 1. Again, you could also, if you wanted, have replaced the y in the original with the sine of x squared, and then you would have had an expression for z in terms of x only. And then you could have found the first derivative of z with respect to x directly. We now want to turn our attention to what are called tree diagrams. Many textbooks use a tree diagram to simplify the process of applying the chain rule in more complicated situations. This is a device or a technique to help you, but it is possible to compute the chain rule without using this method, as we've been doing in the previous 4 examples. Now, tree diagrams can be expanded for multiple variables in multiple cases. They can be written vertically, coming down, or horizontally. Depending on how much room you have on the page, you may choose to go one direction or another. Here's the basic situation we've covered so far, represented horizontally and vertically. This is the tree diagram for the case dz dt is equal to the partial of z with respect to x times the derivative of x with respect to t plus the partial of z with respect to y times the derivative of y with respect to t. In the horizontal, notice that the outside function is the one that is written in the center. This is z as a function of x and y. Because it's a function of 2 independent variables, we have 2 branches coming off of that node. One branch represents the partial of z with respect to x, so you label it that way. The other branch represents the partial of z with respect to y. Because there are 2 branches leaving this node, these must both be partial derivatives. However, when I'm done with this, I label the next one and realize that x is a function of t. Since x is a function of t, which is only one variable, then I have only a single line branching from that node. And that leads me to t, right? So when I'm done with this, I'm labeling each node and each line with the appropriate derivative. This gives me the derivative of x with respect to t because there was only one branch off of that node. Similarly, when we look at the y path, once we get to here, y is only a function of t. And so we have one branch coming off of it, which we labeled dy dt, leading, of course, just to the variable t. Then what we do is we multiply the labels along the branches, not at the nodes, but along the branches. The partial of z with respect to x multiplied by dx dt, the partial of z with respect to y multiplied by dy dt, and we add the 2 together. And this will be the chain rule for this situation. You can do the same thing by drawing it vertically instead. Again, we start with the outside function z, which is a function of 2 variables, x and y, the labels for those nodes. X and y are functions of only one variable, t, which is the label for the final node or the final leaf at the end of all those branches. Let's go ahead now and take a look at another example. Let's take a look at the chain rule for a function of 2 variables composed with 2 functions that are also functions of 2 variables. So in this case, we have a function g of x and y giving us some z value. And in this case, x is also a function of two variables, u and v. Y is also a function of two variables, u and v. This means that when I write the derivative of g with respect to either u or v, I'll have to use the partial notation. Ultimately, g will still be a function of two variables, u and v. That requires the partial symbol, not the italicized letter d. The partial of z with respect to u will be the partial of z with respect to x multiplied by the partial of x with respect to u. Notice we use the partial notation here because x is a function of two variables. Then we have the partial of z with respect to y multiplied by the partial of y with respect to u. We have the same equation, but in terms of the variable v. Let's now take a look at the tree diagram for this one. This one is written horizontally. We find z at the far left in the center. Then it branches at about a 45-degree angle up and down, and z is a function of two variables, x and y. Label the next nodes, the next branching point, x and y. Then label the branch that led to that node as the partial of z with respect to x, because there were two branches leaving z. That makes each of these branches a partial branch, partial of z with respect to y. X itself is a function of two variables. So again, we branch coming off the node labeled x. We have one branch up for u and a lower branch down for v. Because there are two branches leaving the x node, they'll both be partials, the partial of x with respect to u, the partial of x with respect to v. Then we multiply what we get traveling along one pathway. So for example, when we come along this pathway, we end up with this notation that you see there when we multiply them together. If we follow along a different pathway, which comes here and then branches this way, we end up with this notation here. Then we can follow the lower branches, which correspond to the y independent variable. If we branch along the first one, and then we take the u path, we end up with the partial of z with respect to y times the partial of y with respect to u. Then if we follow the y path and then the v path, we will end up with, let me see if I can select another color. I've already used all of those. Green. Coming this way and branching here, the last one will give me the partial of z with respect to y plus the partial of, or times the partial of y with respect to v. How do I apply the chain rule then? The chain rule is going to tell me which path to follow to get my different partials. In this case, if I want the partial of z with respect to u, and let's write that up here, the partial of z with respect to u, then I need to come to all the branches that lead to u. In this case, that would give me the partial of z with respect to x times the partial of x with respect to u, plus the partial of z with respect to y times the partial of y with respect to u. In other words, I'm going to follow the yellow and the purple violet paths to get the partial derivative of z with respect to u. Likewise, to get the partial derivative of z with respect to v, we need to follow the blue and green path. Let's write that one down as well. The partial of z with respect to v is the partial of z with respect to x multiplied by the partial of x with respect to v plus the partial of z with respect to y multiplied by the partial of y with respect to v. As you can see, this can get quite complicated as you're coming down. And you can imagine that there can be all sorts of mixtures of functions of different numbers of variables involved. The tree diagram can really help to make things more clear. You can also represent this information vertically, and you'll see in these two images here that they've highlighted the path leading to u on the left, and they've highlighted the paths leading to v on the right, giving us the partial of z with respect to u on the left and the partial of z with respect to v on the right. Let's now take a look at example 5. In example 5, we have z as a function of two independent variables, x and y, given by the rational function 2x minus y divided by the quantity x plus 3y. X itself is a function of two independent variables, u and v. It is the exponential e to the 2u power multiplied by the cosine of 3v. Y is also a function of two independent variables, u and v. It's the exponential e to the 2u power again, but this time multiplied by the sine of 3v. Go ahead and try to calculate the partial of z with respect to u and the partial of z with respect to v. Use a tree diagram if that helps you to compute these partial derivatives. Pause the video to do the work, then turn it back on. This is an extremely long and difficult problem. I went ahead and applied method 1. I did not use the tree diagram in this case, since the tree diagram is identical to the previous examples we just did. In this case, we need to find the partial of z with respect to x multiplied by the partial of x with respect to u, plus the partial of z with respect to y times the partial of y with respect to u. There is quite a bit of simplification that can occur in these various functions, and there are common factors that can be taken out. You may want to pause the video occasionally to make sure that your work is matching my work. When we focus on the partial of z with respect to u, it eventually leads us down into an expression that looks like the following. 7y over the quantity x plus 3y squared times the cosine of 3v minus 7x over, again, x plus 3y quantity squared times sine of 3v, all multiplied by the common factor 2e to the 2u. This would be an acceptable form for some instructors to leave it. However, if you do in fact substitute for the value of x and y inside the brackets, you will find that there is more cancellation that occurs. That in fact, because of the definitions of x and y, the terms inside the brackets are opposites and they cancel to give us 0, meaning that the partial of z with respect to u is in fact 0. Had we not substituted for the x and the y inside the brackets, we would not have known that. Let's take a look now at the partial of z with respect to v. In this case, we've already computed part of what we need. We have the partial of z with respect to x as 7y divided by the quantity x plus 3y squared. We also have the partial of z with respect to y, which is the same but with a negative sign. Then we multiply each of those respectively by the partial of x with respect to v or the partial of y with respect to v. When we simplify this one, we do again have quite a few common factors. The 7 is a common factor. The quantity x plus 3y quantity squared is a factor. The negative 3 is a factor, and e to the 2u is also a factor. When we factor these out, we get the following expression. This gives us negative 21 e to the 2u divided by the quantity x plus 3y all squared. This is then multiplied by y sine of 3v plus x cosine of 3v. Again, if we replace the value of x and y in the brackets, we can get simplification. When we do this, we find that we get a Pythagorean identity of sine squared of 3v plus cosine squared of 3v, all multiplied by e to the 2u. The e to the 2u that results from the brackets gets multiplied by the e to the 2u common factor on the outside, giving us e to the 4u. So that we end up with negative 21 e to the 4u divided by the quantity x plus 3y all squared. Again, perhaps there's more simplification that can occur, so I went ahead and substituted for the x and the y in the denominator there. You'll see that it doesn't actually simplify that much more. In some ways, it might be better to leave it in terms of u, x, and y. Notice that though we did the partial with respect to v, we ended up with something that was a function of u, x, and y, which is a little surprising. Let's now talk about the generalized chain rule. The generalized chain rule says, what if you have a function of multiple variables, say up to m independent variables, and that each of those m independent variables are also functions of up to n different independent variables. In this case, we give up on different letters and we use subscripts to represent the different ones. So the independent variables of the outside function w become x sub 1, x sub 2, up to x sub m. When we think about each of those independent variables being a function of other variables, those variables are given in terms of t1, t sub 2, t sub 3, all the way up to t sub n. This gives us a way of writing a generalized chain rule. The generalized chain rule gets rather complicated. The partial of w with respect to the variable t sub j becomes the partial of w with respect to x sub 1 times the partial of x sub 1 with respect to t sub j, plus the partial of w with respect to x sub 2 times the partial of x sub 2 with respect to t sub j, all the way out to the last one, the partial of w with respect to x to the m multiplied by the partial of x to the m with respect to t to the j. Let's now take a look at examples of the tree diagram that will help us to simplify the chain rule. We're not going to do ones that are as complicated as the generalized chain rule, but they do get relatively complicated relatively quickly. So it's a good idea to go ahead and practice the tree diagram to help you break apart the different pieces that need to go into the chain rule when we have composition of functions involving functions of multiple variables. We want to go ahead and draw the tree diagram for the case when w is a function of 3 independent variables, x, y, and z, where x is a function of 2 independent variables, u and v, as is y and z. Go ahead and pause the video now, write out a tree diagram, either horizontally or vertically, then turn it back on and we'll compare our work. Let's take a picture and look at the drawing. I chose to draw mine vertically. Note that w is a function of 3 independent variables, so it's at the top center with 3 branches. The branches at the ends are labeled on the nodes x, y, and z. X is a function of 2 variables, So it has two branches coming off of it, and at the end are the leaves U and V. Y similarly is a function of both U and V, so it has two branches as well, and at the bottom they're labeled U and V. We have the same situation for Z. Because W has multiple branches leading from it, all of its branches carry the partial derivative notation. This is the partial of W with respect to X, the partial of W with respect to Y, and the partial of W with respect to Z. Because X, Y, and Z all have two branches leading from them, they are also functions of multiple variables, so all of their branches also carry the partial derivative notation. To find the partial of W with respect to U, follow all the branches that lead to a U leaf at the bottom. They're highlighted here in yellow. This gives us the partial of W with respect to X times the partial of X with respect to U, plus the partial of W with respect to Y times the partial of Y with respect to U, plus the partial of W with respect to Z times the partial of Z with respect to U. To find the formula for the chain rule, to find the partial of W with respect to V, go ahead and follow the gray paths that are highlighted above, leading to all the leaves at the end labeled V. This gives us the same expression as we had previously, but in the second partial factor, it's with respect to V and not U. Let's take a look now at our next example. In our next example, we want to draw the tree diagram for this situation where W is again a function of three independent variables, X, Y, and Z. X, however, is a function of three independent variables as well, not two, T, U, and V. Y is also a function of three independent variables, T, U, and V, and Z is a function of three independent variables, T, U, and V as well. This is going to take a lot more space, so you might as well use a fresh sheet of paper. Pause the video now, then turn it back on, and we'll compare our work. It's a little bit difficult to get this all on the screen at one time, so I shrunk the page a bit and released the ribbon at the top. Notice that this one is written horizontally. In this case, W is at the center on the far left. As a function of three variables, it has three branches leaving it, all using the partial derivative notation. Label the nodes at the ends of those branches, X, Y, and Z. X, Y, and Z are all functions of three independent variables themselves, so they each have three branches coming off of them, and the leaves at the end are labeled T, U, and V for each of those three branches on each of the three independent variables, X, Y, and Z. In order to find the partial derivative with respect to T, what we want to do is go ahead and follow the yellow pathways that we see here. We'll take the partial of W with respect to X and the partial of X with respect to T, plus the partial of W with respect to Y times the partial of Y with respect to T, plus the partial of W with respect to Z times the partial of Z with respect to T. In order to find all the ones that lead to a U, this will give us the partial of W with respect to U. Follow the purple paths to get to the leaves that end in a U. Multiply together the partials along each path, then add all of them up, and that will give you the partial of W with respect to U. Our last branching is going to be done, I guess, what color do I have left? In gray. So come along here and then down here, come along here and then down here, and we'll come along the outside and then down here. Here are the equations that we have for the partial derivative of w with respect to t, u, and v. Notice that each one has 3 terms in it corresponding to the 3 independent variables that w is originally based on, x, y, and z. There are 3 partial derivatives for w because x, y, and z were themselves functions of 3 independent variables. Let's now move on and take a look at example 8. In example 8, we want you to draw the tree diagram, or you can simply look at the picture since I've already got it here in the notes. And suppose that w is equal to x squared plus y squared minus z squared. X is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And z is equal to rho cosine phi. You can see the tree diagram here, though it may not be in your notes. And you can see the chain rule at the bottom in order to find the partial derivatives of w with respect to rho, phi, and theta. Notice that this time, while x and y are both functions of 3 independent variables, rho, phi, and theta, z is a function of only 2 independent variables, rho and phi. Go ahead and pause the video and work this one out, then turn it back on so we can compare our results. This is a really complex, enormously long problem. Let's work our way through it. First, I want to focus on the partial of w with respect to rho. This requires the partial of w with respect to x, which is 2x, times the partial of x with respect to rho, which is sine phi cosine theta. Then we add to that the partial of w with respect to y, which is 2y, times the partial of y with respect to rho, which is sine phi sine theta. Then we add to that, in the black writing, the partial of w with respect to z, which is negative 2z, multiplied by the partial of z with respect to rho, which is cosine of phi. If you notice then that in this expression, we have it in terms of x, y, phi, and theta. The next thing that we can do is we can substitute for x, y, and z to see if this formula simplifies. In this case, when we substitute for x, y, and z, we end up with the partial derivative of w with respect to rho being 2 rho sine squared phi cosine squared theta plus 2 rho sine squared phi sine squared theta, which means that these two terms will combine in a Pythagorean identity to give us 2 rho sine squared of phi. Then we have minus 2 rho cosine squared of phi. You may not recognize it, but the last one is also a trigonometric identity. It's the opposite of the cosine of 2 rho or 2 phi. This gives us a final result for the partial of w with respect to rho of negative 2 rho cosine of 2 phi. Let's now take a look at the partial of w with respect to phi. Again, we take the partial with respect to x, which is 2x, multiplying by the partial of x with respect to phi, which is rho cosine phi cosine theta. Then we add the partial of w with respect to y, which is 2y, multiplied by the partial of y with respect to phi, which is rho cosine phi sine theta. Finally, we add to that the partial of w with respect to z, which is a minus 2z, but the derivative, the partial derivative of z with respect to phi, is a negative sine of phi, which gives us a double negative, creating plus 2z rho sine of phi for the final term. In this particular case, there's no simplification that we can do at this level. However, we could have factored out, for example, the 2 rho cosine phi cosine or rho cosine phi from the first two terms. I chose not to do that, and instead I simply substituted for x, y, and z. After performing the arithmetic and working out the algebra, I found that the first two terms ended up giving me another Pythagorean identity with cosine squared of theta plus sine squared of theta of 1, and a common factor of rho squared sine of 2 phi. Recall that 2 sine phi cosine phi is in fact the sine of 2 phi. It's a double angle formula. And then finally, this gives us, again, the final term, rho squared sine of 2 phi. This gives us, well, 2 of that term, and that gives us the final expression for the partial derivative of w with respect to phi, which is 2 rho squared sine of 2 phi. You could also have that written as 4 rho squared sine phi cosine phi, which would also be acceptable. Finally, we want to take the partial of w with respect to theta. We take the partial of w with respect to x, multiply by the partial of x with respect to theta. This gives us negative 2x rho sine phi sine theta. We add to that the partial of w with respect to y, which is 2y, multiplied by the partial of y with respect to theta, which is rho sine phi cosine theta. In the last term, we're to take the partial of w with respect to z and multiply by the partial of z with respect to theta. However, in the definition of z, it does not depend on theta, making that a constant in terms of theta. So the partial of z with respect to theta gives us 0, and the third term drops out. Once we have this expression, we can substitute for x and y, and we get, quite surprisingly, that the partial of w with respect to theta is in fact 0. Let's take a look at one more example. This is example 9. In example 9, we have w as a function of 3 independent variables again, x, y, and z. The expression for w is xy plus yz. So rather simpler than the last example that we did, which was quite complicated. Y is a function of x, sine x. Z is also a function x, e to the x. First, draw the tree diagram, and then use the tree diagram to apply the chain rule to w. Go ahead and pause the video to work it out, then turn it back on so we can compare our results. Let's examine the tree diagram for this particular example. In this case, w is a function of 3 independent variables, so there are 3 branches from it, each labeled with the partial derivative notation. The branches at the ends are labeled x, y, and z on the nodes. X is not a function of any other variable, so it simply stops at the node x and becomes a leaf. When we follow the path that leads to y, y is a function of another variable, but it's a function only of x, so we only have one branch from it, and instead of using the partial notation, we have the first derivative of y with respect to x using the italicized letter d. Finally, when you follow the path leading to the node to z, we again find that z is a function of only one independent variable, which is also x. So we have one branch, and we use the italicized letter d to represent the first derivative of z with respect to x. Using the tree diagram, we can then follow the paths and multiply together the parts. This gives us the partial of w with respect to x times dx, which is just 1, plus the partial of w with respect to y times dy dx, plus the partial with respect to w, or the partial of w with respect to z times dz dx. Finally, we go ahead and apply the formula using the representations for y and z. The partial of w with respect to x is simply y times 1 for dx just gives us the term y. The partial of w with respect to y is x plus z, and the derivative of y with respect to x is cosine of x. That gives us the middle term. Finally, our last term is the partial of w with respect to z, which is y, multiplied by dz dx, which is again e to the x, since it's an exponential. If we want to substitute for y and z, we can get the derivative, the straight italicized letter d, derivative of w with respect to x, in terms of only x, giving us sine x plus the quantity x plus e to the x, all multiplied by cosine of x, then plus e to the x times sine of x. Now that we have the chain rule, we can take a look at one application of the chain rule where we're able to solve for the derivative of y with respect to x implicitly. This comes in handy when you have functions where it's impossible or very difficult to solve for y in terms of x. What we're going to do in this case is we're going to start with the function of both x and y. This function, if we set it in the plane, in the xy plane where z equals 0, will implicitly define y as a function of x. Let's take a look at one example. Let's suppose that we have a function z of x and y, and this function is equal to y times e to the xy. Now, if we have this function, this is in three-dimensional space, but if we set the z value to be 0, it becomes a curve in the plane. This gives us the equation y e to the xy equal to 0. This does define y as an implicit function of x. The problem is, in this particular equation, there's no way to isolate y on one side of the equation. Since we can't isolate y, then it's difficult to find the derivative of y with respect to x. Now, we did learn implicit differentiation in Calculus 1, and that, in effect, is what we're doing here. Let's take a look at how this would work. What we're going to do is prove that the derivative of y with respect to x is equal to the opposite of the partial of the original three-dimensional function with respect to x divided by the partial of that function with respect to y. Now, why does this work out? Let's take a look at the proof now. In the proof, we have that the derivative of the function is equal to the derivative of 0. In other words, what we've done is we've started with the equation that z is equal to 0, as we did above to settle it into the xy plane. Then we apply the derivative with respect to x of both sides, since we're looking for the derivative of y with respect to x. When we take the derivative of the left side, we have the derivative with respect to x of the function f or z, and the derivative of 0 is, of course, 0. But because the function z is a function of two variables, x and y, we have to apply the chain rule. That gives us the partial derivative of the function with respect to x times the derivative of x with respect to x, which, as we know, is 1, plus the partial of f with respect to y times the derivative of y with respect to x. Again, we're considering y to be a function of x, but x not to be a function of some other variable. In this case, the dx by dx will cancel and become 1, and then we get the partial of f with respect to x plus the partial of f with respect to y multiplied by dy dx. We can solve this equation very simply for the derivative of y with respect to x by moving the partial of f with respect to x to the opposite side and dividing then by the partial of f with respect to y. This method can also be expanded to work for equations that are functions of more than two variables. Let's suppose we have a function w that's a function of x, y, and z. Again, we set it equal to 0 to settle it into the three-dimensional space. And this will define that function. Well, this should be, and this will define z as a differentiable function of x and y. Or we could solve for x as a function of y and z, or y as a function of x and z. If we're looking for the derivative of partial derivative of z with respect to x, then we can apply the rule that we had up above and say that it is the opposite of the partial of the original four-dimensional function with respect to x divided by the partial of that function with respect to z. Notice that in a sense, the partial differentials reverse places on the right side. We can also find the partial differential of z with respect to y by taking the opposite of the partial with respect to y divided by the partial of f with respect to z. This gives us a way of finding derivatives without having to explicitly solve for the variable that we want to take the derivative of. Let's now take a look. Now, of course, I should put in the caveat that when we're doing this, obviously the denominator cannot be 0, since thou shalt not divide by 0 is one of the cardinal rules of mathematics. Let's go ahead and apply this idea now. We want to find the first derivative of y with respect to x, assuming that y is defined implicitly as a function of x by the equation x squared plus xy minus y squared plus 7x minus 3y minus 26 equal to 0. What we've done in this case is we've said that the function of x and y, which of course might be the variable z, is equal to that expression. Now, once we have this, what we want to do is apply the rule that we had up above. Again, we cited z to be 0 so we could get into the xy plane so that we can find the derivative of y implicitly as a function of x. Now let's take a look at our actual function, which is over here in CalcPlot 3D. It's kind of an interesting function. It does have a sort of saddle-like shape there in sort of the middle of the shape, but it grows in all directions coming up from there. It's really kind of a fascinating little shape. What we're doing is we're going to project this image down into the XY plane. In other words, we want to evaluate a contour line where the z value is 0. And we just need that one contour line. So to do that, you would click on the contour plot icon. You would select the first level value to be 0, and you would only choose one contour. Then you can click on Create Plot, and you'll see the curve as it's projected into the XY plane. This is a hyperbola that has been tilted off axis. So when we look at this, what we're trying to find now is the slope of the tangent line to this curve, this level curve, as a function of x. So we're looking for dy dx, a formula for the derivative, which is the slope of the tangent line. Let's come back over here now, and let's go ahead and figure out how to apply the formula. We'll come back up above, and we'll take this formula right here and apply it. dy dx is equal to the opposite of the partial with respect to x divided by the partial with respect to y. Let's write that formula down now. Once we have the formula, we can simply apply it. Again, we hope that the partial of f with respect to y is not 0. If it is, it means there's no derivative at that point. In this case, we're going to take the partial of the original function, but with respect to x. And notice that we have it written up here at the top. So the partial with respect to x would be 2x, and remember, we're taking the opposite, plus y plus 7. Once we have that, then we want to divide by the partial derivative with respect to y, which would be x minus 2y minus 3. This gives us a formula for the derivative of the function where y is defined in terms of x. In other words, the hyperbola. When we're looking at this, the next thing we're asked to do is find the equation of the tangent line at a particular point, at the point 3, -2 in the xy plane. Since we set z to 0, you can also think of it as an ordered triple, 3, -2, 0. Now let's go ahead and evaluate the first derivative of y with respect to x at that ordered pair. When we do this, we're going to end up with 2 times 3 minus 2 plus 7, and take the opposite of it, divided by 3 minus 2 times -2 minus 3. When we work all of this out, we're going to end up with a -11 divided by 4. Because the denominator was non-zero, we know that it does have a derivative at that point. If we think about the level curve itself, which is the projection of the three-dimensional surface into the xy plane, ignoring the fact that it's a little wobbly because it's not precise enough, I didn't take enough data points in CalcPlot 3D for it to be very smooth, it is differentiable, right? So when we're looking at this one, let's go ahead and see where the point 3, -2, 0 would put us. When we look at the point 3, -2, 0, you can see that it's right here in the black dot in the center of the picture, and we've graphed the tangent line that's coming through it. Now the tangent line is going through the point 3, -2, and has slope -11 fourths. Using point slope form of the line, we can write y minus -2 equals slope -11 fourths times x minus 3. This gives us the equation of the tangent line on the level curve at that particular point. Now, this is not what it would look like if we projected this into three-dimensional space. Remember that if we went into three-dimensional space, this tangent line in 2 dimensions would actually become a plane in 3 dimensions. Let's go ahead and click on the center here to see what that looks like. Now you can see the plane extending in the blue color here, and it's intersecting at the point. And it looks like the point has gone to sleep again. So let's see if this will put it back on. Maybe it will. There it goes. All right. So the plane is intersecting the surface at the point, and it's giving us this projection. Let's now take a look at higher order derivatives. Finding the higher order derivatives using the chain rule for functions of multiple variables is actually quite challenging. These are not simple problems, and they go on for several pages. So I have included the solution in the lecture notes so that you can follow along, pause the video if you need to, in order to fully understand the steps of what's happening. In this case, we're going to start with a function of both x and y, 2 independent variables. We're told that x is a function of r and theta, r cosine of theta, and y is a function of r and theta, r sine theta. You should recognize these, of course, from the polar coordinate system. Now, notice that I'm not actually giving you the equation for the function. As it turns out, shockingly enough, we won't actually need the function in order to find a formula for its second derivative with respect to theta both times. If I want the second derivative with respect to r both times, I would have to apply a slightly different process. But the process would be more or less what we follow here. It would just be with respect to r instead of theta. And again, we could also do a mixed partial derivative with respect to theta and then with respect to r, or with respect to r and then with respect to theta. Chances are that this will have continuous first partials, which means that more than likely those mixed partials are equivalent. In order to find the second partial derivative of the function with respect to theta, we need the first partial derivative of the function with respect to theta. So what we need to do is take the partial of the partial. So we're using the chain rule formulas up here in order to find the first partial derivative of the function with respect to theta, which would be the partial of the function with respect to x times the partial of x with respect to theta. Notice we use the partial in both cases because both f and x are functions of more than one variable, plus the partial with respect to y times the partial of y with respect to theta. We can also find the partial of x with respect to theta by applying the partial derivative to r cosine of theta to get negative r sine of theta. The partial derivative of y with respect to theta is r cosine theta. Then we can substitute these expressions into our formula. Notice that we still have the partial of the function with respect to x and the partial of the function with respect to y. We don't actually know what the function is. We just know that that's what would go into those factors. In order to find the second derivative with respect to theta, again, we need to find the derivative of the first derivative. This means the partial with respect to theta of the partial of f with respect to theta, which means we're applying it to the sum of the two terms in the center of the screen. When we look at this, notice that, of course, we have theta in there. Now we have to think about what the partial derivative of f with respect to x and the partial derivative of f with respect to y really represent. Remember that x itself is a function of both r and theta, and so is the partial of f with respect to y. Y does depend on theta, which means that these partial derivatives are also functions of theta being multiplied by another function of theta, negative r sine theta in the first term, and r cosine theta in the second term. Yes, you're right. If they're multiplied together and they're both functions of theta, we need the product rule. So we apply the product rule by taking the partial derivative with respect to theta of the first factor, negative r sine theta, multiplied by the partial of the function with respect to x, plus, now we leave the first factor, negative r sine theta, alone, and multiply by the second partial or derivative of the function, first with respect to x, then with respect to theta. That takes the derivative of the first term. The next line will give us the derivative of the second term. Again, what we're doing is we're thinking of this factor right here as sort of our first function and this one as our second function. And remember that when you take the derivative with respect to whatever variable, this becomes f prime g plus g prime f. And that, in essence, is what we are doing. When we take the derivative of the second term, we're going to take the derivative, partial derivative with respect to theta of r cosine theta, multiply it by the partial of f with respect to y, then add to that, leaving the first factor, r cosine of theta, alone, and then multiplying by the second derivative, partial derivative of the function, first with respect to y, and then with respect to theta. Let's scroll down a little bit so we can see what this comes down to be. When we apply the partial derivative with respect to theta to r cosine of theta, we get negative r sine of theta. And then when we take the derivative of negative r sine of theta with respect to theta, we get negative r cosine of theta. and that gives us the first term. Notice that in the second, it's the second partial derivative of the function, but with mixed partial derivatives. It's not with respect to the same variable twice. When we take this, the next thing we want to do is figure out what those mixed partial derivatives represent. This is going to have to involve the chain rule because both partial derivatives on the inside, the partial of f with respect to x and the partial of f with respect to y, those are both functions of both x and y. So we're going to need partials. The derivative on the outside is with respect to theta. From the work that we did previously, when we were looking for the first partial derivative of the function with respect to theta, we can write that the partial derivative of the function with respect to theta is negative r sine theta multiplied by the partial of f with respect to x plus r cosine theta, the partial of the function with respect to y. Now, one thing that we've done is we have pulled the f from the numerator of Leibniz's notation. It's not a numerator, it's not a fraction, it's an operation, but pretend, down onto the line. Now, how does this help us? Notice that this line here is exactly the line that we started with at the very top. It represents this line here. However, this does give us what we need. How does this give us what we need? It says that the partial with respect to theta of any function is equivalent to this, provided that x is equal to r cosine theta and y is equal to r sine theta. We can apply this rule for the partial derivative with respect to theta to any function by applying it to the functions that we have down here. So we have the partial derivative with respect to theta of the partial of f with respect to x. But this gives us negative r sine theta multiplied by the partial of f with respect to x twice. For the next term, this gives us plus r cosine theta, the second partial of f, first with respect to x and then with respect to y. Then we've got the second term, which we have to apply it to as well. And we end up with the second row that you see here. Once we have this, we can go ahead and apply some algebraic manipulation in order to simplify it. Let's scroll down so we can see the simplification. When we look at the simplification, we've got r cosine theta multiplied by the first partial of f with respect to x as our first term, minus r sine theta times, and then this was the formula that we applied for the partial derivative with respect to theta, which is minus r sine theta multiplied by the second partial of f with respect to x both times, plus r cosine theta times the second partial of f, first with respect to x, then with respect to y. Applying it to the second term gave us negative r sine theta, first partial of f with respect to y, plus r cosine theta, and then we applied the rule for how to take the partial with respect to theta, giving us negative r sine theta times the mixed partial, second derivative, of f with respect to y then x, plus r cosine theta, second partial of f with respect to y both times. Now, of course, the next thing we need to do is simplify it by distributing the common factor. Once we get to this point and we've simplified and multiplied out all of our common factors, note that if the mixed partials are in fact continuous, then they must be equivalent to each other. That would make this second derivative, first with respect to y, then with respect to x, and this second partial derivative, first with respect to x and then with respect to y, the same value. In that case, because their other coefficient factors are the same, r squared sine theta cosine theta, you can combine them together into two terms, and you could use either mixed partial for your final form of the second derivative, partial derivative of the function with respect to theta both times. Notice that in all of this process, we have never actually defined what the function f is. We simply know it depends on x and y, but we do know the definitions of x as a function of r and theta and y as a function of r and theta. The chain rule can be quite challenging to apply, so I hope that you will take some extra time and care on the homework for this particular section. In the next section, we'll be talking about directional derivatives and gradients. A directional derivative is one that is not parallel necessarily to either the x-axis or the y-axis, but instead going off in a different direction. I hope that you'll join me for the next video in this series.